In this part, we want to discuss the volume of a hollow solid. Now look at the diagram here. We have the red curve, y is x squared. We have the blue curve, y is square root x. Between the red and the blue, we have this region. If we revolve this region about the y-axis, now immersion, what will we get? All right, we will get a solid that the outer surface is red in color, kind of like this. All right, but in the inside, it is hollow. All right, the inside surface is in blue. Right, it's kind of like the shape of a cup. All right, but then the middle part here is hollow, is empty. All right, so this revolution, the element will be this part. All right, we take this part and we revolve it about the y-axis. Now what do you get is a ring instead of a disc. All right, the ring, the inner surface, the inner radius is in blue, while the outer surface is in red. It will be something like this, right? The original element is this one, and of course there will be thickness for this particular ring. So the volume of this ring is the surface area, is the cross-section area. This one, the cross-section area will be pi the red x squared, and then subtract the whole. The whole will be pi in blue x squared, and that we multiply this to the width, the thickness of the ring, and that is dy, and we integrate from the smallest y to the largest y. Alright, we do the integration. So that is the volume of this hollow solid. So in practice, first of all, we need to have x squared. In red, the x squared is y, so it's fine. In blue, we change to x squared, so x squared should be y to the fourth power. Alright, keep this in mind. And the boundaries, this of course is the origin. This will be the point 1 and 1. So the integration will be from y is 0 all the way to y is 1. Alright, so we can set up the volume in this way. The volume of this hollow solid is the integration. We have pi x squared. Subtract pi x squared. 1x is in blue, 1x is in red. Alright, and then dy. We'll do it from y is 0 to y is 1. Alright, and then if you replace all the x's with y, it becomes x squared. The red one, x squared is y. The blue one, x squared is y to the fourth power. So that will be this integral, and that goes to y squared divided by 2 minus y to the fifth power divided by 5. Alright, the integration from 0 to 1. Alright, and that answer is 3 pi over 10. That is the volume of this hollow solid. Alright, so the difference between hollow solid is that for the integration element, it is a ring. Alright, it is pi x squared minus pi x squared, the outer radius minus the inner radius. Alright, and then we integrate from the smallest y to the largest y if we rotate about the y-axis. Alright, this is how we deal with a hollow solid. Alright, so let me show you another example here. We have the blue straight line, y is 2x. We have the red curve. Now the region bound between the blue line, the red curve, and the y-axis, we try to revolve it about the y-axis, right? Now, but pay attention, in this part is partly hollow, partly filled, partly hollow. The part above here, in part 1, is hollow, alright? And then part of them is filled. It's a solid object, right? In number 2, right? Number 2 is a complete solid object. You will see when you rotate this one, you will get an extended, a cup like this. But then the blue hole is only into a part of it, right? It only goes into a part of it. It does not go to the bottom. So you have to split it into 2 parts. The first part is a hollow solid. The second part is a filled solid. So let's deal with the second part. The second part is easier. Alright, of course you need the boundary. Alright, let's take a look at all these points. Alright, this is where you have y is 0. Now this point y would be minus 3. Alright, and how about this point? Alright, we solve the blue and the red equation. We observe that this point is 3 and 6. if you solve between the red and the blue, alright, we have x squared minus 3 equals to 2x, alright. So that means x squared minus 2x minus 3 is 0. So x is minus 1 or x is 3, alright. So it is on the right hand side, so x is 3. When x is 3, y is 6. So this one, y equals to 6, right? So in part 2, the volume will be from minus 3 to 0, alright. All these are x squared pi x squared dy, alright, pi x squared dy. So you need to express x squared. After rearrangement, you have x squared equals to y plus 3, alright. So that would be from minus 3 to 0, pi times y plus 3 dy. That is the volume of the second part. And that goes to pi y squared over 2 plus 3y, alright, from minus 3 to 0. And that equals to 9 pi over 2. Alright, so that is the second one. The part at the bottom, right? The part right here. We know that it is 9 pi over 2. Now for the top part, it is the hollow solid, right? For the top part, the element of integration is this one. You will get a ring. You will get a ring with the outer diameter. The outer radius is in red, and the inner hole will be in blue, right? So the that will be pi, and then the red x squared subtract pi times the blue x squared, alright, and we integrate with respect to dy. We start from the smallest y being 0 all the way to y being 6, alright. This is number 1. So the red x squared, we already have it, y is 3, so we need the blue x squared. We have the x squared will be y squared divided by 4, alright. So we can have this one equals to pi from 0 to 6, y and 3, alright, and we subtract from it, the blue x squared will be y squared over 4, alright. We integrate with respect to y, and that goes to y squared over 2 is a square, y squared over 2 plus 3y minus 1 over 12 y cubed, alright. We do it from 0 to 6. So we put the 6 into it, 0 and 6 into it. So this part goes to 18 pi. Alright, 18 pi. 18 pi is the volume of here, right? Without the hole. Alright, that is the volume of this part. So altogether, we can have now the total volume will be 1 plus 2, and the answer goes to 45 pi divided by 2. Alright, that is the total volume of a solid that is partly hollowed and partly filled. You must divide them into two parts, right? Because part 1 is a hollow solid, but part 2 is a complete filled solid. There's no hole in part 2. Alright, so there's a bit different. For part 2, this is the red x squared, mind you. Alright. Alright, so this is the second example here. Now, there's a third and a final example. We want to investigate the volume of a torus. The torus is a circle, right? But it is revolve about the y-axis. So it's kind of like the shape of a ring, but it is circular. Alright. So now the outer radius, the radius of the hole is capital R, but the radius of the ring itself is a small r. So we have this circle. The equation is like this, right? The center, the orange point will be r and 0. The green radius is the small r. So we have this equation. Now, all we need to do is to get the, first we find the integration boundary. That will be y is minus r at the bottom, y is capital R on top. That is the small r, right? That is the radius of the circle. Now, when you do the rotation, we discovered we have to split the x. We have to recover the x. We notice that the circle will come in. We have to split the equation of the circle into two parts. The first part, let me color it in blue. All right. The first part is like this. We have x equals to r squared minus y squared. We take the square root, but there's a plus minus square root. This part is the plus. All right. It's the capital R plus something. So that is the blue x, alright? Noticing that this is the capital R, x equals to R. So all the blue thing is on the right hand side of the orange, so the blue x is R plus something. And then we have this green x, alright, on the other side is the green x. All the green x will be on the left hand side of R, so all the green will be capital R minus R square minus y square, take the square root, alright, that would be in green. Now we have to distinguish between red and green because each of these elements, when you rotate about the y-axis, you get a ring. The inner radius of the ring is in green, while the outer radius of the ring is in blue. Alright. So that's why the volume of each of this ring is pi blue x square minus pi green x square. This is the blue x square, this is the green x square, and the thickness is dy. Alright, the thickness is dy. We integrate from the smallest y will be minus r to the largest y is r. So this is the volume of the torus, alright, from minus r to r, pi x square, and then minus pi x square, one in blue, one in green, alright. That is the volume. Now it's funny to investigate the x square minus x square in blue and in green. The x square in blue, you will have x square will be r square and small r square minus y square and twice r square minus y square. But then the one in green will be r square plus r square minus y square, and then minus 2r and then r square minus y square. So you see, if you take the blue subtract the green, you will have most of these terms cancelled. You will end up with pi and then 4 times r and then r square minus y square. Right, this is what you have if you cancel most of the terms there. Alright, when you have the blue x square minus the green x square, you have all these terms cancelled. Alright, only remains will be 4r r square minus y square. Alright, the capital R is a constant, so we use integration by substitution. I have to let y is r sine theta. Alright, so that we have dy will be r cosine theta d theta. When when y is minus r, theta will be minus half pi. When y is r, theta is half pi. Alright, so this integration becomes pi from minus half pi to half pi, and that is capital R and then small r square. I don't have enough space. Alright, let me extend it here. So that is let me carry on here, right? So we have 4r, we just copy it, and that is r cosine square theta, r square cosine theta d theta, alright, from minus half pi to half pi. Alright, now cosine square theta, once again we know the integration is 4 pi r square r, and then integrate minus pi over 2 to pi over 2 cosine square theta d theta, and that is 4 pi r square r cosine square theta d theta. The result is theta over 2 plus 1/4 sine 2 theta. Right? We do it from minus half pi. From half pi to minus half pi. Right? And this answer eventually goes to 2 pi square capital R and then small r square. This is the volume of the torus. well, due to space limits, I skip some of the steps doing the integration of cosine square theta. Maybe you can, finish it as an exercise on your own. How do we arrive at the integration of cosine square theta becomes something like this, right? You can catch it up on your own. But this is the answer of the volume of the torus. It is a hollow solid. We take the outer radius in blue and the inner radius in green, alright? So happen it can be easily cancelled. And then after integration by substitution, we can have the result. Alright, so this is the end of the part 3.